A poet writes in verse, whereas a mathematician writes in verse, like a backwards poet would. Today we're looking at inverse functions. So today we're looking at basically mapping what used to go in and then would produce some output as the new input to reproduce my old output. So what I'm going to say is I have 5 that, let's make it a little bit bigger. So 5 goes into the machine. The machine does some stuff to it and it comes out a 3. Now, the inverse of that would be to take the 3, put it into a machine, and it spits out a 5. So this would be the function f of x, and this would be the inverse function of x. So as we look at inverse functions, we just want to basically think of an inverse relationship as mapping what used to be my output values back to their original input values. So I like this picture here where it looks at apples, right? Apples are going into this function and it spits out lemons. If I put in lemons into my inverse function, it will spit back out the apples. So this is mapping what used to be my x's to my y's, and I would take what used to be my y's and get back to my x's. So here's an example looking at an xy table here. So x values on top, y values on the bottom. I plug in -2, it spits out 4. I plug in -1, it spits out a 2. Plug in 0, spits out a 0, etc. So all of my y's become my x's in my inverse relation. When I put this x value in, it will spit out what my original x was. So now y's become the input. So now I'm taking my output as my input. Oops. And then what used to be the input, old input, and they're not drawing well for me today. What used to be the old input is now my output here. So basically I'm able to map back to where I started. If I did this function and then plugged those outputs back into its inverse relation, it'll bring me back to where I started. So basically we're trying to map back and forth between these two things when I'm using an inverse function. So this is my original graph. So let's do a couple different color points. Here we got orange here. We'll do green. Blue sticks with blue. Got purple here. And we got a lighter purple here. So when I take these points, which I'm going to color the same way here. So orange, that used to be over here, now gets remapped to being over here. This point used to be -2, 4. Now over here, it's 4, -2. So again, I'm remapping each of these things. So orange remaps like that. I'd have my green one remap like this. And each of them are being reflected over the line y equals x. So here's my reflection over y equals x. We got our purple value and then our light purple. So we see we are mapping these things over the reflection of the line y equals x. So this would be the graph of the inverse relation. To find an inverse relation, basically what we're going to do is we're going to take our original equation, we're going to swap the x and y values, and then we're going to resolve for y. So I'm going to say this started with y equals blah, 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 x stuff. And the first thing I'm going to do is I'm going to swap these two. So I'm going to say, okay, well now x is equal to, let's see, we'll keep the constants set like that, 2y minus 4. And I'm trying to solve for y. So how would I solve for y? I want to get rid of my constant, so I'm going to add 4 to both sides. So now I get x plus 4 equals 2y. To get y by itself, I would divide by 2. And now I'm saying, okay, that's my final answer. Y is equal to x plus 4 over 2. If you wanted to represent this as x over 2 plus 2, that's fine as well. It's just the same thing in another form. I personally would leave it like that. If you want to write 1/2 x, that's fine as well too. So the inverse relation for this y equals 2x minus 4 is y equals 1/2 x plus 2. So when both of these are functions, we would say that they're inverse functions. When I do have two inverse functions, I should be able to take f of g of x and g of f of x, and it's going to spit out, actually I should do this on top here, there we go, and they should both spit out x. So again, this f raised to the negative 1 is f inverse. So when we see this, it means f inverse. So here, I just want to verify that this thing here and this thing here are inverses, right? This is the one that we just found its inverse. So we took this, we found its inverse, and now here's how we verify that they're inverses. I'm going to take this red thing, I'm going to plug it into the green, and I'm going to take the green and I'm going to plug it into the red. So I'm going to try and notate this with colors below. So I have the green thing plugged in over here, the red thing plugged in over there. So this is my, green part being plugged in. And I'll say that's bigger green. Here we have the larger red. So again, I'm taking this chunk here and plugging it into where I had my x right here. So that's why we have 2 on the outside, and then I see the 1/2 x plus 2, and I still have the minus 4 sitting on the outside. I do my distribution here, and I get x plus 4, x minus 4, and now here it just simplifies to being x. So we have confirmed that we get what we were looking for over here, which is that it's just going to equal x. And then I want to do the same thing, but this time for f inverse of f of x. So now I'm taking the red thing, and I'm plugging it into the green thing. So where I used to have x here, now I want to plug in 2x minus 4. So 1/2 of 2x minus 4 is, and now I do my distribution, so x minus 2 plus 2. This simplifies to give me my x again. So here we have verified our inverse functions. If I want to write an inverse model, I am basically going to start with some equation. The equation we're starting with here is looking at the length of a spring relative to the weight attached to it. Here we're weighing a watermelon. So as I look at this here, I have a relationship L equals 1/2 W or 0.5 W, however you want to talk about it, plus 3. So when I look at this, I want to find, well, what is it going to be for W then? So to solve for W, and so this is just ever so slightly different from the last two we did. You can literally swap your x and y here and then solve for it that way. But really what I'm just trying to do is isolate the W. So here I isolated L, now I want to isolate W. So I'm going to start out by saying L equals 1/2 W plus 3. Again, if you want to write it as 0.5, whatever floats your boat, it's the same thing. Here I'm going to subtract 3, so I get L minus 3 equals 1/2 W. To get the W by itself, I'm going to multiply both sides by 2. So now I get, to make sure we're doing the entire side here, 2L minus 6 equals W. So now I have the inverse function, I have the W thing by itself. When I'm looking to solve for this now, and it tells me, okay, you place a melon on the scale, total length was 5.5. So now it's giving me an input for my L value. So that's just going to go right in here. So my L input here is going to be 5.5. So I'm going to say 2 times 5.5 minus, 6 equals the weight. So to solve for this weight here, I do 2 times 5, which is 11, minus 6, which is 5. So I get the weight of my watermelon here was 5 pounds, and that was the weight which stretched my spring to 5.5 inches. Here we're looking at finding inverse functions for our non-linear functions. So this is just curvy stuff. So we've got our quadratics and our cubics that we're going to take a peek at. So here I have on the left a value which is just squared, which gives me a parabola, and here on the right I have a value which is cubed, and that gives me this kind of like disco guy, finger pointing up here, finger pointing down here sort of looking graph. And when I find the inverse of these things, they may or may not exist. So when I say may or may not exist, I'm looking at x squared here. So if I take x squared and I reflect it over, so this I'm going to color in 2 different colors here. I'm going to do the left half of this thing in orange, okay, and that is this part right here. I'm going to do the right half of it in purple. It's going to be this half right here, which becomes this half right here. So the reason I'm splitting this into 2 halves is that when I flip this over, this y equals x axis, I don't pass my horizontal, I don't pass my vertical line test anymore. So this thing is not a function. So x squared does not have an inverse function. So when I flip this thing over, again, it does not pass my vertical line test, so this thing does not have an inverse function. If I wanted to restrict my domain, like instead of talking about all of x squared here, I was just talking about the left half. So I'm just talking about x values less than or equal to 0. Then I could get an inverse function. It would just be the orange thing. So again, if I restricted my domain, so if I said, something like 4 x values less than or equal to 0, it would look like the orange thing down here, and it would have an inverse. Likewise, if I wanted to say 4 x values greater than or equal to 0, then again, I'm just talking about the purple part here. So again, each of those specified for a domain restriction would be okay for an inverse function, but as a whole, it is not. The reason being is when I take the square root of something, I'm going to get plus or minus. So when I plug these values in, basically, let's look at 1 for example, right? What is the square root of 1? It's plus or minus 1. Negative 1 times negative 1 gives me 1, and 1 times 1 gives me 1. So when I plug in these values, I'm going to get 2 answers that spit out. So when I'm looking at this, we just want to be careful for that. If I have a domain restriction, then it's okay. Otherwise, it's not a function. Our odd degrees, so 3, 5, 7, 11, whatever, are going to be totally fine in terms of what my inverse function is going to look like, because this passes, no problem, and this passes, no problem. So here, in terms of my inverse function, this thing passes my vertical line test, so I'm good to go. So here, my domain can be all real numbers, and I see that the red here is my inverse. So if I had x to the third, the inverse of that would be x raised to the 1/3. So as I look at this blue is my original, red is my inverse. Again, here we have blue is original, red is inverse, but I really need to split this thing between orange and purple to talk about it as a function. Otherwise, it is not. If you note here, this does not pass the horizontal line test, but this one does. My blue function here, my blue function here. So does not pass horizontal, does pass horizontal, does not equal a function, does equal a function for the inverses. So just keep that in mind, and we're going to look at that in more detail in a second. So let's actually find one of these inverses. So the first thing is I'm going to say, okay, let's look at this thing. So I'm going to say f of x equals x squared. Now, for simplicity's sake, and I'm saying I have a domain restriction, x greater than or equal to 0. Okay, so here's my big key domain restriction. So for this one, I'm just going to change to writing y equals x squared. So if you want to write f of x, it's not wrong, it's totally fine, but typically we just swap this out. So now I want to solve when I swap these two variables. So now, as my first step, again, just substituting so I'm not writing f of x every time. So now I'm just swapping these, so I'm going to say x equals y squared. I want to solve for y. So how do I solve for y? I would take the square root, so I would take the square root. So now I'm going to say plus or minus the square root of x equals y. So when I'm looking at this, keep in mind what my domain restriction gave me. So here, my domain restriction, since I said only x values greater than 0, I have now restricted this thing to only being the positive value. So when I said x is greater than 0, I took this parabola, so let's say it looks like this, so it's rather poorly drawn, and I said, okay, x value is greater than 0, that's just this stuff over here. So when I do my inverse function, that's just then going to be this stuff right here. So again, if we imagine this thing was flipped over, it's just going to be this part of the graph. So now, in terms of my answer, it's just going to be y equals the square root of x. Oops. There we go. So not the negative version. If I change this, okay, if I change this problem, and I said instead I gave you x needs to be less than or equal to 0, then it would just be this part over here. So then it would just be the red stuff right here, just this part of the graph. For that, it would just be this part of the inverse, and that would be negative square root x. So again, this is just two different domain restrictions. This problem was specifying the blue one here. But if I changed it slightly and said, okay, for domain restriction, instead I want x is less than or equal to 0, then it would be the negative thing. So here's where we actually define what our horizontal line test is, which is that no horizontal line intersects the graph of a function more than once. So just like our vertical line test, but now horizontally. Then we're able to say the inverse of that function is itself a function. So over here, if I wanted to run a line through like that, I intersect here and here. That does not pass the horizontal line test. Therefore, it will not pass the vertical line test. And we see that here. For the odd function, this does pass my horizontal line test, right? Try and draw a straight line through anywhere on this blue graph and you'll only hit 1 point. Even though it may look a little bit cloudy there, if you zoomed in, you would see it. It's very hard to tell, but you would only ever hit 1 point. So now what does that mean? If I flip this thing around and then did vertical for the red thing, I'm always going to pass. So if you pass the horizontal, then your inverse will pass the vertical, and therefore it actually is itself an inverse function. To find an inverse function, we're going to look at this one here. So let's start out by writing y equals 1/2 x to the third minus 2. So again, just swapping out my f of x for y. Now my actual first step is to just exchange my x and y, so I swap those, y to the third minus 2. And then from here I start solving for y. So now to solve for y, I would add 2 to both sides. So x plus 2 equals 1/2 y to the third. I'd want to get this y to the third by itself before I take the cube root, so I'm going to multiply both sides by 2. So multiply both sides by 2 here. So now I get 2x plus 4 equals y to the third. As my last step here, I'm going to take my cube root. So I'll take the cube root over here. And so now for my final answer, I get y equals the cube root of 2x plus 4. This is all underneath my cube root sign here. So this is my final answer. If I wanted to switch back to my f of blah notation, I would represent it as f inverse x equals, and then I have my cube root of 2x plus 4. So we just want to make sure our radical sign extends over everything here. And we're good to go. So when we are looking at this thing, we see this would have passed the vertical line test, therefore this would have passed the horizontal line test, therefore this will pass the vertical line test. It's inverse. So here we have determined the inverse of this function. If we want to graph this, we could. Any value we want is fine because we have a domain all real numbers. We're good to go.